All right, lesson 7.5, Taylor series. What is it? It's a BC topic. In this section, you'll be finding polynomial functions that can be used to approximate transcendental functions. Those are the fancier functions that aren't polynomials. Could be exponentials, trig, all bunch of stuff. If p at x is a polynomial, which is simple, used to approximate something more complicated, a function, they must contain the same point, that x value being c. So the polynomial and this tricky function would share a point at some x value. And to be a better approximation, they would also share the same value of the derivative at that same. And they would share the same for the second derivative and the third derivative. And then putting this all together forms a series. And this is called a Taylor series when you use a polynomial to approximate a trickier function. Now, if you use a point where x equals 0, then it's called a Maclaurin polynomial. So a Maclaurin polynomial is just a special Taylor where the x value you start with and plug in we use is at 0, which makes it easier. If it's centered at any other number but 0, it's just called a Taylor. All right, turn the page. We need to memorize, this right here. So we start with the point, the derivative at the point, x minus c, the second derivative at that point. So the y value of the point, the derivative at there, x minus c. And there's a pattern with the factorial that the more we practice, we'll see it. So we're going to use the definition of a Maclaurin polynomial to find the fifth degree. And that just means that we go to the fifth derivative and then expand it as such. So in this case, f at x equals e to the x. So what does e to the 0 mean? It's 1. The derivative is e to the x. Plug in 0, it's 1. I think you get the idea here that whenever you take the derivative, it stays the same. Plug in 0, it stays the same. So all the way down, you take the derivative, it stays the same. Plug in 0, it stays the same. Now the key is to remember that, what was it, the page before in the box. And so it starts with f at c. So it starts with this right here. So it starts with 1. And then the derivative at that is 1. And then it's x minus c, which is x minus 0, or just x. And that's over 1 factorial, but we don't need it. The next one is 1, and now it's x minus 0 squared over 2 factorial. And then it's 1, because we're following this. We're at the third one. It's x minus 0 cubed over 3 factorial. And I know we could simplify it, but I want to see the pattern. So again, we start with 1, and it's x minus 0 to the 4th over 4 factorial. We're going to do it one more time. X minus 0 to the 5th over 5 factorial. And that is what's called a Taylor expansion. So e to the x is more complicated. We can approximate it using this polynomial, using this pattern. And if you want to see the pattern again, think of it as this is what matches the exponent and the factorial number. The exponent and the factorial number. And all along, you're going to go x subtract wherever it's centered at. So in this case, it's centered at 0. And then the first number are these numbers that we come up with. So let's try this again. So this gives a good approximation for f at x equals e to the x. By extending the pattern into an infinite series, it becomes exactly correct instead of an approximation. So if I simplify this, it's 1. This is x to the 1 over 1, which is just x. This is x squared over 2 factorial, or 2. Or x cubed over 3 factorial. And so to write it as a general term, it'd be x to the n over n factorial. The general form of a Taylor and a Maclaurin polynomial can be extended to Taylor and Maclaurin series. So here we have a series, and that you can see they're the same, except this c value is just 0 as we go across. These formulas allow us to form a power series for functions that cannot be written as geometric power series. All right, turn the page. Example number 2. I know I kind of wrote all over it, but it is what it is. So we're given a function cosine x. And then we're centering it at pi instead of 0. So we're going to plug pi in and see what the answer is. So the value of cosine at pi is -1. The derivative of cosine is negative sine. Plug in pi. The y value there is 0. The derivative of negative sine is negative cosine. Plug in pi. And it would be -1, but the negative and the negative make it +1. You kind of see a pattern happening here. The derivative of negative cosine is positive sine. At pi, the answer is 0. The derivative of sine, we're just going to start all over again. The derivative of sine is cosine. And that answer is -1, and it would repeat over and over again. So what's the fourth order polynomial? What's the pattern that we start with? So start with -1 plus 0. Now, of course, 0 times anything, the answer would just be 0. So we actually don't need to write, but we'll write it out for the pattern. So it's 0, and then it's x minus pi to the 1 over 1 factorial, even though that answer is 0. The next one, the number 2, would start with 1. And then it's x minus pi to the 2 over 2 factorial. Now I know it's 0, but we'll stick with the pattern. 0, x minus pi to the 3 over 3 factorial. And then the last one, -1, and it's x minus pi to the 4th over 4 factorial. That's expanding it to 4. This is simplifying it. So if I simplify it, I get -1. 0 times anything is 0. This is going to be plus x minus pi squared over 2 factorial. That's 0. This is negative instead of positive, and it's x minus pi to the 4th over 4 factorial. And then you can see the pattern that's going to happen after that. If I want to approximate cosine 3, in fact, if I saw the next pattern, it'd be plus, it'd be x minus pi to the 6 over 6 factorial, if I was following the pattern. Then it'd be 8. It'd be subtracting, alternating. To find the value at cosine at 3, plug 3 in for x, and you can use the polynomial to approximate it. And then you'd plug that in your calculator. I'll do it for you. And you get negative 0.989857 and so on. That's the approximation. If you really did cosine 3, it's very close to that value. Use the definition of a Maclaurin series, which means it's centered at 0, to do this work. So f at x equals sine x. So Maclaurin means it's 0. So the value at 0 of sine is 0. The derivative is cosine. At 0, cosine is +1. The derivative of cosine is negative sine. At 0 is 0. The derivative of negative sine is negative cosine. At 0 would be 1, but it's -1. Negative cosine would be negative sine, which is positive. And then we just start it all over again. So what would we do to put these values into the series? So we start here with 0. And then we start with 1. And we go x minus 0, which is just x. So if it's a Maclaurin, do I need to go x subtract 0? No, just x. That's to the 1 over 1 factorial. Then the next value is 0. Again, I'm just going to follow the pattern. That's x to the 2 over 2 factorial. The next one is negative 1. And that's x to the 3 over 3 factorial. The next one would be 0. X to the 4 over 4 factorial. And then positive 1 again, x to the 5th over 5 factorial. So if I simplified it, we don't need the zeros. So it'd just be x. This would be x squared over 2 factorial. This would be negative x cubed over 3 factorial. That's 0. That would be plus x to the 5th over 5 factorial, and so on. And then if I want the general term for that, if I look at, it alternates, so it's negative 1 to the n, and then it goes, well, this is, what did I make a mistake? This is, so this should be 1, this should be 3, this should be 5, I think I put a 2 in there actually, this would be 7, right, if I was following the pattern and so on. So it's odd numbered, so we're going to go x to the 2n plus 1 or minus 1. So in this case, minus 1. That makes it odd. So if I plug in 1, the answer is 1. And then the denominator has the same thing. So it's 2n minus 1 factorial. All right, turn the page. Find a power series centered at 1 if f at 1 equals 2. And then this shows the derivative is always going to be that factorial. So we're already given that f at 1 equals 2. F prime at 1, the derivative at 1, would be 1 factorial. That's what it's saying. The derivative, the second derivative at 1, would be 2 factorial, because whatever the derivative is, that's that factorial. The third derivative at 1 would be 3 factorial, and so on. So how do we start this power series? Start with this value, f at 1, which is 2. And then we have 1 factorial, x minus 1, because it's not 0, to the exponent 1 over 1 factorial. Well, you're going to see what's going to happen to the 1 factorials when you do that. The next one is going to be 2 factorial, and it's x minus 1 to the 2 over 2 factorial. The next one's 3 factorial, x minus 1 to the 3 over 3 factorial. And so you can see these cross out. And then what you're left with is, we started with 2. And then it's just n minus, or x minus 1 to the n. And that's it. All right, Mr. G Math over now. Let's do our homework together, assignment together.